Good afternoon, everybody. So it's a pleasure to introduce Tamara Kolda for our second plenary talk for this afternoon session. Professor Kolda, so she did her PhD in Maryland in 1997, is a senior member at the Sandia National Lab, and for SIAM, and this is a SIAM conference, most importantly, she is a member of the board of directors. She has been a long-time associate editor of SIAM Journal of Computing, and most importantly, there's a new journal, Mathematics of Data Science, where she is the first editor-in-chief launching this journal, and she will say something at the end of her talk about it. So thanks, Tamara.
Thank you. Greetings, everyone. Thank you for coming this afternoon. I want to thank the organizers for the invitation to speak. It's a real pleasure to be here. This is joint work with Sam Sherman, who's here. I'll show her picture at the end, and you will recognize her. I want to say thank you for the invitation to come and visit Switzerland. It's a lovely country. I've been to Zurich before, but I've never got to explore. So I've come a bit early and did some exploring. And if you're here afterwards, I especially recommend Zermatt. I really loved it there. And these are my own pictures. I had a great time. All right, so on to tensors. So first I'm going to tell you about tensor decomposition and give you an application to sort of help to convince you that it's interesting and important. Then we'll specialize to symmetric tensors and empirical moments from statistics and show how these connect. So first I'll talk a little about low-rank tensor decomposition. Well, that's kind of funny. Huh. Sam, technical assistance. It looked just fine a second ago. Oh, it just crashed. That's all right. We can switch. We can switch to mine if need be. Oh, here we go. Hopefully it doesn't crash again. All right.
Yeah, I hope.
All right. So what is a tensor? A tensor is just an array in my lingo. So a tensor, you know some tensors, a vector is a tensor of order 1. So we use D here to denote the order. Oh, this thing crashed. Well, anyways, OK. Matrix is order D equals 2, and a third order tensor is D is 3. Yeah. Thank you. And so this is just the number of indices to show the tensor. And we can go to higher orders, 4 and 5, and so on. And so these are our tensors. They show up in a lot of applications. If you have an application that has data, you might have a tensor. And so they became very popular, especially in the 90s, in the area of chemometrics, where they're useful for fluorescence spectroscopy, where they take readings that are emission by excitation. If you do it over multiple samples, it becomes possible to determine the different amino acids in the samples that you're measuring. In neuroscience, we'll talk more about an example today, which is measuring individual neurons over time over multiple trials. We've done work with data from the Chicago crime reports, which are online. We can look at a tensor that is the day of the crime, the hour of the crime within the day, the neighborhood of the crime, and the type of crime, and do analysis on that to see trends in crime. We've looked at, we'll talk today about symmetric higher order empirical moments, which are useful in machine learning. People have looked at taxi cab data. So New York City puts all its pickups and drop-offs and times available for even for Lyft and Uber, so you can analyze that. It's millions upon millions of records. I have a colleague who looked at sports data, so looked at the statistics of basketball players over multiple seasons, so multiple statistics, multiple players, and there's a lot of missing data there because not every player plays every season, so it makes it interesting. We looked at cyber traffic, social networks, and even in optimization, there's actually some quite older papers that look at the properties of the higher order derivative. So Newton's method uses the Hessian, that's the second order derivative. You can go higher and use that information optimization. So that's a place where actually symmetric tensors come up. All right, so the context of the tensor decomposition, it's a mathematical and statistical tool for data analysis. So basically, we want to express our data as a sum of parts which are simple to understand. And so we'll explain what that means. And so our mathematics and statistics plays a role in the foundational methods and making the algorithms fast and efficient. And then these things are used in a lot of different applications, including filling in missing data, just visualizing what you have, which is what we'll mainly show today. And you can also do clustering and so on. And these have related concepts for matrices. So you have the singular value decomposition, the eigenvalue decomposition, principal component analysis, independent component analysis, and the like. So if you are familiar with those, then this should look somewhat similar. If it's not, that's OK, because sometimes knowing those things just confuses the issue. All right, so we want to decompose the tensor into pieces that we can understand. So throughout the talk, we'll call our data tensor X. And this is just an n by n by n tensor, so order 3, mostly because that's the easiest for me to draw. But everything I say will go to higher order 4 or 5. Tensors even go up to order 1,000. I'm just going to say all of the sizes are the same, n by n by n. But most of what I will say for the non-symmetric part relates to tensors that are some arbitrary size n1 by n2 by n3. And the examples I'll show you will have different sizes for each dimension. Then we want to construct some model tensor. In our case, this will be a low-rank model tensor. That's the same size. And then it has structure. So it's going to be the sum of pieces. We call those components in tensor lingo. And each of those are the same size. But the secret is they have structure. And so the structure is that they are what we call rank 1 tensors. So each tensor is the outer product of 3 vectors of length n, or in the D-way case, d vectors of length n. And that's where we can sort of figure out what's going on with the tensor. So the rank 1 components, say we have the outer product of 3 vectors a, b, and c. All this means is that the ijk entry of their outer product, which we denote with this cross in a circle, is ai times bj times ck. That gives you the ijk entry of the outer product. So very simple structure. If it was just a matrix, there would just be no c, and just be a times b transpose. And you can go to higher order. You can go to order d, but then it just gets kind of messy. So I have vectors a1 through d, and I'll take a superscript 1 cross a superscript 2. It gets hard to say in a talk. That's why I like to just use ABC. And then you can get the I1, I2, dot, 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 ID entry by taking the IK entry of vector AK and multiplying them all together. But we won't really do the D way. We'll just stick with 3 for simplicity here. All right, so we are going to be looking at the so-called Kandicamp parafac, or CP tensor decomposition, which is basically what I've just told you about. We're going to try and take our data tensor, say a 3-way data tensor, and find a low-rank model of it. By low rank, we mean it's the sum of very few of those components. And so we have a bunch of A's, B's, and C's. So we'll take the outer product of A1, B1, and C1. That's component 2. Then A2, B2, C2. That's component 2, and up to component R. How to choose R is a very hard problem that I won't actually talk about today, except to say that in practice, we just try different values. And I'll try and make a few comments. But figuring out the right R is sort of an open question. And since I deal with real data and we have noise in any case, we don't worry too much about it. And then we typically assume that the number of components is very small compared to the overall size of the tensor. I'll just say a little bit about the history. So the CP was first proposed in some papers by Hitchcock in 1927. He was a professor at MIT. He was, among other things, the thesis advisor of Claude Shannon. He's a pretty decent Google Scholar profile for having been writing papers in 1927. And the papers are actually, about tensors, are fairly readable. So this paper here, I can look at this expression and understand it. I don't expect you to, but if you work in tensors, if you just stare at this a bit, you can understand it. And this is the expression of a tensor as a polyadic, or a polyadic as a sum of products. And then that was sort of, in some sense, lost to history. Completely independently in a different area, it was reinvented twice. Once by a pair at Bell Labs. They called it canonical decomposition. This is Doug Carroll, who's well known in the psychometrics community. And then a person named Gigi Chang, who I would say is a hidden figure. She was just sort of this name on this paper, but I became curious who she was one time when Siam sort of wrote out the name. And I said, who is this person? So I actually contacted folks that worked at Bell Labs at the time. So Fan Chung Graham, she never responded to my email faster than when I asked her about Gigi Chang, because she and her husband, Ron Graham, actually knew Gigi really well, and they put me in touch with her former husband and niece, and eventually her daughter, who got me this picture of her working with Doug Carroll. And I've talked about her in some other lectures, and people said that they actually knew her. They knew of her through her code. So she was a software developer, because back then, software was women's work, and that sort of was relegated to the women, which is so backwards, from how it's perceived today. And, I think maybe it could be everyone's work. And then Richard Harsman, at the same time, invented it and called it parallel factors. So when I first started reading in this field, I got very confused about this Kondo-Kemp and this parafact, and eventually come to realize they're the same thing. And so in around 2000, a guy named Hank Kears, who's popular in tensors, said, let's just call it CP. We won't favor one or the other. And then it was sort of reverse engineered to canonical polyadic, which sounds so much more mathematical, I guess, around 2010. I'm not sure exactly who had the first paper that used that, but Pierre Camon and Lieven de Lathauer and others had papers that started calling it that. And that sort of just came out of the woodwork, but I like that. So that's the many meanings of CP. So I'm going to give you just sort of a motivating example from a paper that I did with a group at Stanford, in particular spearheaded by a student named Alex Williams, who finished his PhD in neuroscience, is now at the stats department at Stanford as a postdoc. And so they had data that comes from this interesting machine that they invented, which can measure the signals from multiple neurons at once. This very blurry picture that you really can't see. Here's a wire coming down to the mouse. This device is attached to the mouse's head. It's very small. And then each moment in time, they get an image of multiple neurons lighting up in the mouse's head. And then quite a bit of work takes a single neuron, and there's a lot of overlapping signal here, but they do a lot of work. This yellow arrow is 2 years of work. They get intensity over time of each neuron. So that's one neuron. The cool thing about there is they can do multiple. So here's sort of that one neuron as a vector, where yellow is sort of the most active. And then we actually had 282 neurons, and then over 111 time bins. And so that's the mouse moving through a maze over time. Then they actually had the mouse run this maze over and over and over again. Their ultimate goal is to understand learning of the mouse. So it ran it once, it ran it again, it ran it again. And so they said, what do we do with this data? And so they can put it into a tensor. And the basic idea is we have 282 neurons that are being imaged, 111 time bins, and then 300 trials. And so what happens is the first 75 trials, the mouse comes to the middle, and it should turn right or left. If it turns right for the first 75 trials, it gets a treat. Then they change the rules, and then it should turn left to get the treat. It has to sort of figure this out by trial and error. And then that goes for like 125 trials, and the last 100 trials, it should turn right again to get the treat. So it has to sort of figure this out as it goes. In the paper in Neuron, which I mentioned before, it's actually even a more complicated setup, and they also do a monkey controlling a cursor with its brain and other types of stuff. And they compare it to matrix type techniques like PCA, which is very standard in the community, and independent component analysis, and find that the tensor technique works much better. So I always think it's a nice idea to look at your raw data. So here's 9 of the 282 neurons. What we show here is for each neuron, there's 300 trials. So we show the activity in this thin line. There's 300 thin lines in each of these plots. And then the thick line is sort of the average. And so what you can see here is the neuron up at the top, neuron 26, is active at the beginning and then pretty much off towards the end. This one's sort of off at the beginning and active towards the end. And you can see different behaviors. This neuron 117 is sort of interesting because sometimes it turns on and sometimes it just sort of stays off. And so there's clearly different types of behaviors. So if you're the neuroscientist, if you collected all this data, you could just stare at 282 plots like this, or maybe do some sort of analysis. So this is where the tensor analysis comes in to make sense of a huge pile of data. So we did a rank 8 decomposition of this data. So it's neuron by time by trial. And so we get out a bunch of vectors. And the way that we then visualize what we get out is we look at each of the vectors. So the first vector A corresponds to the individual neurons. So the lines in red are the ones we just showed. And so there's 282 neurons here, and it's represented as a bar chart. So that's sort of the activity of each neuron. And the line in the middle is 0. Then we have time. So the dashed line there is 0. And this is the time profile for the first factor. And we just plot it as a line because it's smooth. I didn't smooth it out. It just came out smooth. That's the inherent property of the data. And then the most confusing one is the last. That's the 300 trials if we plot an individual dot for each trial. It's green if the mouse turned right. It's orange if the mouse turned left. We fill in the circle if the mouse got the treat, and the circle is open if it didn't get the treat. And so, and then you can see these red lines where they change the rules. So here, it gets the treat if it turns right. And then they change the rules, and it's sort of wondering what's going on for a while. Eventually, it realizes it needs to turn left, and mostly does that. And then they change the rules again. It seems to clue in a little more quickly this time. So that's what's going on there. But then we have, we show that as sort of one row. That's the first component. But we actually have 8 components of this tensor. And so the neuroscientists saw that. You know, you can stare at this, what's going on. I'll give you some highlights. If we look at the third component, so here, we can see that this one is active towards the end. And then if we zoom in on this piece, what was interesting about that is it separates when the mouse turned right, when it got the reward versus when it didn't. So there's sort of almost a straight line between the open circles and the closed circles. So they can tell whether or not it got a reward. And so presumably the neurons that are lighting up have to do with getting a reward and being happy to get the treat. And then if we look at the last one, which is also active towards the end, this is clearly separating the direction of the turn, the orange versus the green. And so this just happened. The tensor just got a bunch of numbers, which were activation levels, and it sorted all this out. And there was actually some others that sort of indicate turn, and then some mystery components like this is just, I don't know, background thinking or something. So I like to spend my spare time wondering what these different components mean, and I really identify with this mouse, and the fate is not good for this poor guy. The neuroscientists only kind of like this, and the reason is that we have negative values here. What they gave us was sort of how intense each neuron was, and we're giving them back negatives, and it doesn't really make any sense to them, and I think with good reason. So I was excited about this, but it's very hard to interpret. What does negative neuron activation mean? So we have sort of a little quick aside. You can switch out the objective function. So we've created something called generalized CP tensor decomposition. And so the standard metric is you're trying to get this low-rank tensor that minimizes the sum of squared errors. But you can change that and just have a general function f, and just pick what you want here. And I always say I'm not going to judge you by your choice of f. I like you no matter what f you pick. When you work with analysts, they sometimes have some idea of what they want to use. But you can also have things that are statistically motivated. So sum of squares is the first one. Then you have the Poisson, which is for count data. So if your x is like 0, 1, 2, and so on, you're basically predicting the lambda of the Poisson variable, the mean. And you can use x hat minus x log x hat to sort of test your fitness If you have 0, 1 data, so coin flip data, Bernoulli data is your tensor, and your model is predicting the odds of seeing a 1, you can use the function we have here. And then there's also something called beta divergence, which is not coming directly from a probability distribution, maximum likelihood estimate, but is also very popular. And I'll show you results for beta divergence on that data. It gives a non-negative decomposition. And now the folks, the neuroscientists, were much happier. So now we have the reward, getting the reward is here, and not getting the reward is here. And so I guess you could look at these two sets of neurons and say, this one is about being happy, and then it's very low here. If I look at the red, which is sort of my landmarks, it's very low here. And you can sort of see which neurons are about disappointment and which are about happiness. Likewise, for turning right gets its own thing, and turning left. And then here, there are some, this only turns on for left, and this only turns on for right, but this one's on for both. So like that may be something to do with, I have to make a turn, and then which neurons are actually activated that can also specify which direction. So that's how we can start to make sense of that. So that's sort of the benefit of using tensor decomposition. So now I'm going to switch gears to the symmetric case, which has a lot of applications. A tensor is symmetric, let me just tell you what it means, if all its entries are invariant under permutations of the indices. So a symmetric matrix is Aij equals Aji. A symmetric three-way tensor is Aijk equals Aikj equals Ajik, and so on. There's 6 different permutations. For d-way tensor, there's d factorial, different permutations you can do. And the total number of unique entries in a d-way tensor of dimension n is n plus d minus 1 choose n, or roughly n to the d divided by n factorial. So there's this nice paper by Jiwang Ni, and he talks about symmetric tensor decomposition. There's this nice little example as like concrete examples. Here's a 3 by 3 by 3 tensor. So the first sort of frontal slice is shown as that first 3 by 3 block. The middle is the second. The back one is the last. It actually only has 10 unique entries shown here. And so you can see sort of -3 is here, here, and here, but that's really just one value in the symmetric tensor. A symmetric tensor we can decompose into symmetric rank 1 parts, and so it's basically the same as before, except instead of A, B, and C, we just have A and A and A. And the ijk entry of the three-way product, which we'll now just write as shorthand A cross 3 in the exponent, is AI times AJ times AK, is that IJK entry. And you can also do it for a D-way. You just take D copies of A and outer product them. So symmetric CP tensor factorization is just a basic idea. If you want to find a low-rank CP model with each entry being symmetric, so that means you have to find a bunch of A vectors. So A1 goes with the first component, A2 goes with the second component, up to AR is the third component. And so we'll write this as the sum of this outer product, and we can use the shorthand AJ cross 3. This lambda thing has appeared. This is sort of a scale factor. So I could take the sort of, I could normalize the A's and then take out what is to norm 1 and then take the product of those norms, and that would be AJ. The interesting thing is for odd tensors, you don't really need that lambda to be explicit, but for even, if you want to do any subtraction, you need an explicit lambda, because otherwise when you power things up, it's always positive. So I'm going to have lambdas in this. It's a funny thing in tensors. You can have the lambdas or not have the lambdas, and it causes all sorts of numerical nightmares if you don't handle them correctly. All right, so if we look back at that tensor again, we can ask things like, what is its rank? So the rank is defined as the minimum number of components that sum up to give you back the tensor. And so that's just formalized here. So it's the minimum R, such that when you sum up the D-way outer product of the R vectors, you get back the original tensor. And for this one, we just showed the rank decomposition is here. I always like to give something that if you're bored, you can just multiply that out and just convince yourself that's the rank. So the lambdas are 2, 5, and -1, and then the vectors are shown there. For any given tensor, finding the rank is known to be NP hard. You can, over R, you can find the, or sorry, just in general, you can find the typical rank over C. So that's sort of the rank that you get with probability 1 due to some well-known results. In practice, however, we just do a lot of trial and error. And everything I'll do will be decompositions over R. So for symmetric tensor decomposition, there are a few different approaches. There's Waring decomposition, which is mostly useful if you have sort of a noise-free situation. There's algebraic methods based on Grosvenor bases, which is basically just numerical root finding, and you can do it just the Grosvenor basis way or numerical way. It's a nice paper by Nee. And then I've done some work on just what I call the direct optimization formulation, mostly because that's my numerical background is optimization. And these tend to be fast, if in many ways less robust. So if we want to do that, what do we have to do? So the reason I like optimization is you just need a function and a gradient, and you're off to the races. So here our function is we're just trying to minimize the difference between the model tensor X and the low rank, the data tensor X and the low rank model, where X hat has this structure. So I just have to find the lambda and A's that make up this X hat. And so the norm is just the sum of the squared entries. And so I'm just finding the sum of the squared errors when I take the difference between the two tensors. And then we can just compute the gradients. So here we have the gradients with respect to the vectors AJ, and the gradients with respect to the lambda j's. So these are these complicated looking formulas. I'm going to try and convince you they're not that bad. So with respect to AJ, it's minus the D, which is the order, times the lambda j, times this funny thing, which is a tensor times same vector. So it multiplies the tensor X times this vector AJ D minus 1 times, which is just defined over here. It gives out a vector of length n. The ith entry of that is just Xij k times aj times ak summed over all j and k. And then it's plus d times lambda j times a weighted version of the inner products of all the different a vectors. So this gives you the gradient with respect to the a's. You can also do the gradient with respect to the lambdas. Here we have x times aj to the dth power, which is almost the same, except for that we're doing it summing over all indices rather than all indices but 1. So it's the sum over xij k times ai times aj times ak. So we can compute the function value and the gradient, and then we can just plug that into our favorite optimization method. So this could be something like steepest descent or any other first order method. I really like limited memory BFGS is sort of my personal favorite. And then you can just run this in MATLAB. In the tensor toolbox for MATLAB, we have classes that handle symmetric tensors. And so I'll just say do CP symmetric optimization with rank 3. It runs for 91 iterations, which takes 0.2 seconds. And it gets this solution here. That solution I showed you before is this. They look different, but it's just actually a scaling. So this is 1 minus 2 minus 1. If you stare at this, you're like, oh, that's the same pattern. So if I just rescaled it, it's the same thing. And if you multiply it out, you get back that same tensor. All right, so we want to use this in a context that is motivated in machine learning. So what if we are given a field of points? So we're just given a bunch of points, and we want to try to understand the distribution that they came from. And we're just going to assume that our sum is a mixture of Gaussians. So here we have 3 Gaussians. They're kind of overlapping a bit in where their points go. And our goal is to try and find these means. And that's what we want to try and do with our tensor decomposition. For this talk, I'm just going to assume those means have norm 1, which makes all sorts of nice things work out, and see what we can do with symmetric tensor decomposition. So first of all, if you look at this point cloud, you say, well, that one's easy. It kind of looks like there's 3 Gaussians. You can almost see that from where you are. So I'll color code it so it's sort of easy. But when they're overlapping, it's a lot harder. And so when they're close together, it's hard to sort out what's going on. And so here's sort of what it might look like if we color code them by which Gaussian they came from. So we want to be able to try to solve harder problems like this where it's overlapping. And so just to reemphasize, it's easy. You can still use tensors, but it's relatively easy. There's a number of methods I can find these means if it's split apart, but it's a lot harder when they're close together. And for these pictures, there's 1,000 of these little dots. We're just doing n equals 3, so it's actually so you can visualize it. And then rank 3, so 3 Gaussians are being summed together. We actually want to do much larger n and p and even somewhat larger r. So what's the formal setup here? So we're going to use this empirical moments to try to figure this out. So we have a bunch of observations. So each z sub L is one of our dots in that picture. So we have p dots. Each is a vector of length n. And so we can put those into a matrix we'll call z that's n by p. So that's all our observed data. And we can actually calculate things like the first empirical moment. That's just what we know as the mean. So we take the sum of all the z's and just take their average. You can do the second order moment. So that's the cross product, also known as the covariance. You just take the average of all the covariances of the individual vectors. And then you can go higher. You can do third order moments. And so here, this is going to be the tensor that we're going to work with x. We're going to take the third order moment, which is the average of the outer product of the observation vectors. We're going to try and get the average of those three-way outer products. And what this means is the ijk entry of our third order empirical moment tensor is 1 over p times the sum over all the observations indexed by L of zil, zijl times zkl. So it's basically taking entries from the same entry and multiplying, same observation vector and multiplying them together, and we're going to take the average. And so the rank rank R symmetric decomposition of this tensor X can recover those means. Let's see, did I say everything there? Oh yeah, and so the interesting thing to note, which is why a lot of this stuff works, is if each of these vectors came from a multivariate normal with the with zero mean and the sort of identity covariance, then their higher order moments would be 0. And so that sort of makes a lot of magical things work out later. All right, so we're going to set this up. We're given a bunch of observations. We're going to create our data tensor, and we're going to assume that each observation here comes from a normal distribution centered around one of the means, which we're calling AJ. So that's one of these dots. And that's normal distributed with some constant standard deviation sigma for everybody. And so what we show here is the circles are the true means. And so we have this x that's our data tensor. And then we want to recover our model, which looks very much the same, sort of the outer product of some vectors. But r is very small compared to p. So here r will be 3, because we want to find 3 means. And then there's also this lambda. Don't worry too much about that. And so the squares here are what was recovered when we calculate this x and then do a third order symmetric tensor decomposition. The a's that we get out from that symmetric tensor decomposition are the squares that we see there. And so they're pretty close for this highly overlapping set. And then there's this theory that even if your data doesn't come from a sum of Gaussians, almost any density can be approximated by a mixture of enough Gaussians. And so that's what makes this useful even if your data doesn't truly come from Gaussian distributions. So what does this cost? So if we have our data tensor that's n by p, we want to compute this moment tensor. This is where things get kind of nasty, and where a lot of people don't use these methods, is that just computing this thing, I have to take this three-way outer product. So I have to create something that's n by n for the three-way case, or n to the d for the d-way case. And I have to do that p times. So it's p times n to the d work just to form this x. And this takes n to the d storage. So if I did n was 128 features, d is 4, so a fourth order moment, then the storage for that is 2 gigabytes. That's not even that big. And then if you do 512 and d equals 3, that's 1 gigabyte. So very quickly you run out of space. If you just have n as 100, and you do d equals 3, doesn't take very much time, as we'll see. But once you start to grow, it doesn't scale. So we have the optimization function and gradients. The other thing to notice is that that's just the pre-work to compute this. And then every optimization step cost r times n to the d. That's because of these tensor times same vector pieces. So this becomes prohibitively expensive. So the question we had is, can we avoid that? And the answer is we can. We don't ever have to form that x tensor, that data tensor explicitly. We can just work directly with the z's, and then we're trying to compute this a. And so we never have to form x or x hat. We can just find the a sort of magically. So here's our explicit method. Here's our implicit. Instead of calculating the norm of x, for example, we can take z transpose z, so that's that n by p matrix, to the dth power. And then E is the vector of all ones. That just means sum up all the entries of z transpose z raised to the dth power. And we can do similar tricks for all the different pieces. And we reduce the work from p times n to the d to just set things up, just to compute this norm once, and n to the d work every iteration, to n times p squared here and np here. And so the most expensive thing is this npr thing. So we go from p n to the d work to order npr work. So exponential in d to d disappearing. That makes a huge difference in the cost. So let me sort of demonstrate that difference. So here's just sort of a simple example. Here, I'm projecting it down to 3D, but it's actually n is 100. So each of these points is in 100-dimensional space. There's 1,000 of those points. We're going to do the sum of 5 Gaussians, and we're going to do the third order moment. And so the circles are the true means, and the squares, which you can barely see, are the recovered means, and they're close, so it works. And then the normal method, I mean, it's pretty fast. It takes, less than 0.3 seconds. The first dot doesn't come up for a while because that's that work just to calculate x. But if we use the implicit method, we've reduced that time quite a bit. So this is p times n to the d work just to even get started, and this is npr work per iteration. So it's a lot faster. But for this problem, it's not a huge difference. If you scale up n, say we do n is just 300, we already start to see that it's gotten quite a bit more expensive, because this is only increased by a factor of 3, the implicit method, because n went up by 3. But this went up by n cubed. So 3 to the 3 versus 100 to the 3 becomes much more expensive. Now we're at 5 seconds versus much less than a second. And we can recover the answer the same either way. Now, if you increase your dimension, so you want to do the fourth order moment instead of the third order, here I had to shrink n down to 75 to make this compute in a time that was reasonable. And same other setup, 1,000 points, 5 Gaussians. And then we'll do the fourth order moment. We can see that this explicit method, which is n to the d, so now d is 4, and we're getting up to about 9 seconds. But the implicit method hasn't changed at all. It's still way less than a second, because it doesn't depend on d. And we get the same answers either way. So just a different way of calculating things that avoid some big in-between expense. If we did a problem where n was 1,000 and we had 10,000 observations, it's 8 gigabytes just to store that data tensor. And I didn't even form it because I had to do that 10,000 times and add those all up. So I didn't even show that one here. But the implicit method still gets there in just 11 seconds. You can't see the true and recovered means here. I'm just going to tell you that it was correct. Here's our 10,000 points. One problem here is that there is this factor of p, which is the number of samples. And here we went up to p is 10,000. So there's this time here to get to the first iteration, which is just this computing the norm of the tensor, np squared cost there. That's actually a constant. We don't really need to do it, but it's annoying. And then this depends on p. So this is p is 10,000. What if p was 1,000,000 or tens of millions, which happens in these large-scale data science applications? What can we do in those cases? What we can do is a stochastic style of optimization method. And these are extremely powerful techniques in data science. They come up in a variety of places. I'll give you my 30-second tutorial on stochastic gradient descent. We just want to minimize some function f of x. The normal gradient descent type method is just